So my name is Andreas Hellander. I worked with Linda and Brian in the StochSS project for a long time. And if you were here yesterday, you met Linda and Brian then. Otherwise, they're here now. And then today we also have Fredrik Wrede, who is a PhD student in the project, about to finish his degree soon. And today, Fredrik will talk a little bit about advanced sort of model analysis tools, model exploration and model inference. And then do a tutorial, which I think you will be able to follow along to learn how to use inference and exploration capabilities inside StochSS Live. So with that, I give the floor to Fredrik.
Okay, thank you. So I will start immediately to share my slides first. Right. Let's see if I can switch. Yeah. Yes, Andreas said, my name is Fredrik Wrede, and I'm a PhD student at Uppsala University in Sweden. I work at the division of scientific computing, and as also Andreas mentioned, I work a lot with techniques and tools for model exploration and parameter inference of the type of models that we are been demonstrating yesterday, and we will demonstrate a bit more today. So yeah, this is part 2 of this tutorial. So yesterday, Linda had some introduction to the types of models that we are using. And Brian also had a demonstration tutorial of StochSS Live and how you build and develop your models and how you can do some basic analysis of your models. So let's actually see here if... So Jamie and Max, were you at yesterday's session? You could, wherever you do, answer in the chat or live right here. It's just good for me to know if you were here. How do I bring up the chat window?
So it's a yes and a no.
Okay, thanks. Okay, so then I know. So what I will do today is to demonstrate what model exploration is, and then give a small tutorial on how we can do this in StochSS Live. I will also show some demonstration of parameter inference inside StochSS Live. And these types of the methods that we have been developing for this has been developed by me, Andreas, and Prashant Singh. And then Prashant will take over, Brian will take over and have some more advanced topics on StochSS Live. Okay, so before we go into the live tutorial, I need to give you some, at least, background on what we mean by model exploration and parameter inference of biochemical reaction networks. So in model exploration, the objective is really to try to search for different qualitative behaviors that are being produced by a model. And we do that by varying different conditions in the model, the parameters, in the form of parameter sweeps. So giving some initial design or some priors of the parameters, you can sample parameter points, and we then simulate those, and we like to observe what kind of behaviors, dynamic behaviors, are being produced by the model. So this is quite complex if you're having models that are very high dimensional or complex in general with many parameters. Since these kind of workflows will become massive, basically, you will have to deal with very high dimensional parameter spaces, and you will have to create or simulate a lot of data to get some kind of feeling of your model. So why would you like to do this? Well, the main reason basically why we are using models is to gain or yield new hypotheses about the inner workings of the phenomenon that we are trying to model, right? So essentially what we want to do is to find potentially interesting behaviors inside the model and try to understand and get a better feeling of the model that we are trying to implement. And this is typically the case when you have little priori information about your model. And this could, for example, be when you're early on in the modeling phase, or that you just lack some information about the model and don't have a lot of experience. It could also be that you perhaps would like to do parameter inference in the future, but you don't have the data yet. So you're trying to sort of tune your model as a pre-processing step. So that is model expiration, and I will demonstrate a bit in the live tutorial how we do this, but essentially what we do, which is more sophisticated than regular parameter sweeps, which is that we are using machine learning techniques to sort of aid and make it more easy to explore the vast amount of data that are generated by these kind of computational workflows. And then parameter inference, I won't say that much about this because there is actually several sessions in this conference that specifically go into this. So I can really advise you to go into one of those if you're interested. But just basic concept here is that in what we're trying to do in parameter inference is that giving some observed data, some real collected data from wet lab experiments, for example, we would like to fit or infer the model parameters to that data. And the Bayesian approach to this is that we would like to quantify the uncertainty of our parameters of the model given conditioned on the observed data. And this quantity right here, this distribution is called the posterior distribution. And this posterior distribution is proportional to the likelihood, the data distribution, times our prior beliefs about the parameters. Now, in the type of models that we are dealing with here, most often, except for the most trivial cases, this likelihood function is not available for us. It's intractable and we can't compute it. So we can't do exact inference in this way using this formula right here. Instead, what we do is that we turn to approximate methods. And there is something called likelihood-free inference, which is an approach that is based on that we are using simulations to approximate our likelihood right here. And we are doing this by taking samples from a prior parameter. We then take that parameter, we simulate those, we get that simulation output, and we compare that output to our observed data by some kind of discrepancy measure. And if that discrepancy measure is below some threshold, we deemed it to be accepted as an approximate sample from the posterior. So we are basically approximating the posterior. And some kind of hot topics right now in likelihood-free inference and estimating posteriors is that you use machine learning and specifically neural networks to estimate this. And this is something that we are working on a lot. It's specifically, we have been working on convolutional neural networks to do this for us. And quite recently, or very recently, we published a paper in Archive, that a preprint that does Bayesian neural networks to do this kind of stuff. So I will demonstrate inside StochSS how you can use this. StochSS have all you need to do this kind of stuff using a package, Python 3 package called sciop that we have been developing. So sciop contains the methods that we have been working on, as well as a general package for distributing and doing this kind of workflows in parallel using a third-party software called Dask. So I will demonstrate how you can use sciop inside StochSS Live. Okay, so I will stop sharing and go now into the tutorial. So if you want to tag along on this, you can go to your browser and go to live.stochss.org, as you can see up here. What you can then do is either, if you haven't already created an account, I highly advise you to do so. Brian demonstrated yesterday how you could do this, but basically what you do is to link it to a Google account, and then you should be fine to start modeling. So I already have an account, so I will just click here, and because I have cookies around, oh, actually, I have to sign in anyway. I didn't know this. So I signed in with my Google account. Okay, so then we are at the home page of StochSS Live. And here you can see that we can either browse your current project or create a new one. You also have a tutorial here, and this is some of the things that Brian demonstrated yesterday. So for this tutorial, and to show off model expiration and model inference, I will create a new project. I'll call it SIAM part 2. Okay. So then we get directed to the project page. And as you can see here, we can add models and we can add workflows. So yesterday, Brian showed us how you can create models, how you can build your models. I won't actually show that today, but I will use an existing model. So I press this one right here. And from this list right here, we have several examples that you can use and play around with whenever you want. For example, Brian demonstrated the toggle switch yesterday, so that one you have right here. For this session, I will focus on a really simple problem, which is the dimerization problem here, model. Great, and then we can see that it's now under our models right here. And if we just click on this model, we can see the model editor page is a bit slow right now. Maybe it's because I'm sharing. So yeah, this is where Brian yesterday demonstrated how you build up your models. So right here, you can see that we have two variables of interest, one monomer and one dimer. And you set the initial conditions, whether you want to use a deterministic way of using concentration or our discrete stochastic version using populations, hybrid, etc. And then we have the parameters. We are focusing on two parameters here, which is the reaction rates for creating from two monomers. We create one molecule or dimer, and the dimer can also do the reverse reaction and go to two monomers. So a really simple model that we will work with. Let's go back to the project page. There we go. So what we want to do now is that we want to create a new workflow for this model. So we press new workflow using model. And this is also where Brian yesterday demonstrated some of these workflow, for example, ensemble simulations and parameter sweep and the Jupyter notebooks for the above mentions as well, and also for 2D parameter sweeps. So down here, you can see that we have sciop model expiration and sciop model inference. So these are the workflows, Jupyter notebook workflows that are integrated with sciop. So I will start with demonstrating model expiration. So that will direct us directly to a Jupyter notebook. And as you can see here, this will automatically create a Jupyter notebook for us where we have defined the corresponding model that we want to use right here with the associated parameters, species, reactions, etc. Here we have some convenient imports that we need to use to define the model, as well as defining what kind of solver you want to use. So let's go ahead and press Shift-Enter to run this cell. And this one as well to define the class for the model. And then we initiate this class and call it model. What we can do then, for example, is something similar to what Brian showed yesterday, which is if we call model, actually, we have to do this first. We have to define what kind of simulation parameters we want. So here I just give the solver I want to use and some other keyword arguments, solver, the number of trajectories. The default one here is 100, but for today I'm going to use just one. We can go ahead and run this model. And then just do configure. Okay, so that run. And then we call res.plot. I don't know why it's so slow right now. I think it's called plotly, right?
Yep, that's right.
Yeah. So here we can just see what the default parameters would look like if we simulate one trajectory from that. And here you have all sort of interactions that you can do. You can remove the diamond, for example, etc. So let's move on to model expiration. So there are three things we need for model expiration. We need a corresponding simulator. And what it's actually one really good thing with the implementation that we have done is that we have considered everything to be as a black box. So the simulations will act as a black box. The model expiration toolkit doesn't really care about the underlying model. It just wants to have some data to do the model expiration on, and it is required for this data to be dynamic in the form of time series. So it's a black box model expiration. So we need a simulator to be able to actually simulate the data. And then we need some kind of design or prior to define where in parameter space we would like to sample parameters and simulate those. And then since usually the output from simulations are quite high dimensional, for example, for this model, we are using 1 to 100, 0 to 100 with a time step of 1. So it will be a 100 dimensional 2D array in this case, since we have dimer and monomer. So instead of using that raw time series, we would like to extract some summary statistics or features. And yesterday, Brian called this feature extraction, which also is, I use that term as well, since it's more of a, I would say, machine learning term or data analysis term. So those three things are the ones that we need. So sciop comes with something in the utilities right here. It's a Gillespie 2 wrapper, and Gillespie is the package that contains all the solvers that is under the hood for StochSS Live. And to create a simulator which is have the suitable dimensions for the output, etc., for sciop, we have a wrapper here that you can call get simulator on the model directly, and this will automatically create the kind of simulator that we need for sciop. We have a similar wrapper function to get the parameter expression array from the model in the form of a numpy array directly. So we call these two. And here we can see that the expression array tab isn't working. This is very annoying. So I can't autocomplete. This is our parameters, the default parameter. And we will use this to define our prior, or our design of how we would like to sample from parameter space. So as I mentioned before, sciop is built on Dask as a parallel package to distribute over clusters or do multiprocessing to sort of parallelize these kind of workflows that we are doing here. And here I would like to demonstrate how you can do it by creating a local cluster using Dask. So we call Dask client, simply like this, that will create a local cluster. This is strange.
Fredrik, I don't know if this is helpful at all, but before we've had issues if there's spaces in the names of your project.
Mm-hmm.
Did you try this before with a simpler name?
You mean the project name might conflict? I removed the previous one, but I had the same name for the project.
I see. That was my only guess.
So if I go back here and create a new project with a different name.
You can rename the project too if you'd like to just go to files.
Let's